Let's start with a blank board for the mean value. We're going to get into the mean value theorem, and then I'll jump into the notes here. The mean value theorem, let's see if we can't make sense of this. If f is a function, if we let f be continuous on a closed interval and differentiable, let's shorten that, on the open interval, then there must exist a c, so that's the there exists. That's the then. There exists a c in that interval, in that open interval, such that f prime of c, so the derivative, the slope of the tangent, equals the slope through the point AF of A, B, F of B. Let me give you a picture of this. So let's say we have something like this. Okay, here's A. I didn't draw that very good. That's terrible. Let me get a little more curvature. Oh gosh, the struggle is real. Let me go from here to here. From this A to this B. Notice, first of all, it is continuous. I can draw this without lifting my pencil, right? Imagine this keeps going. Smooth and continuous. It's closed, continuous on the closed interval. Is it differentiable? Well, as long as it's smooth and continuous, then it's differentiable, right? We can take the derivative on that open interval. Then it says, let me look at the right-hand side of this for a minute. There must, well, let me get to the exist part. But the right-hand side says the slope, right? Notice this is y2 minus y1 over x2 minus x1. Here's the slope of that secant line through A, f of A, comma B, f of B, right? That's the slope, right? Whatever that positive slope is. What the mean value theorem is saying is there must be some c in there whose derivative, whose slope of the tangent is equal. And there it is, at least graphically there it is. Does that make sense? So the slope of the tangent, there's some c in that interval where the slope of the tangent is equal to the slope of the secant line through those points A, B. So let's get into the notes here. And that's what it is stated right there with another picture. And notice it has to be continuous and differentiable as I stated in that very concise notation. So let's do this first example. Let's just determine whether it can be applied to this function f of x equals x to the 4/5 on 0 to 1. So let's go ahead and take the derivative, and you'd get 4/5 x to the 4/5 minus 1 negative 1/5. In other words, the derivative is 4 over 5 x to the 1/5, so 5th root of x. Notice that the the original function has to be continuous on the closed, right? So yes, it works. Is continuous on 0 to 1. In other words, I can plug in 0. I could take 0 to 4/5, I get 0. I could take 1 to the 4/5, I get 1. It's fine. And anything in between it, it'll be fine. It'll be continuous on there. And then, is it differentiable? And it's got to be differentiable on the open interval. Well, 0 would be a problem. It would not be differentiable at 0. There's the derivative. Notice I can't divide by 0 there on the derivative. But that's not a problem because it's open anyways. It's open anyways. And we could throw in anything up to 1 too, right? It'd be fine. So it is continuous on the closed, and it is differentiable on the open. So I say, yeah, the mean value theorem is okay, or applies. It applies here. You can apply it. Okay. Let's do another one and see if we can apply it on this one here. We've got I'm going to distribute this first before I look at it. I got x cubed minus x squared minus 2x, and we're trying to determine if the mean value theorem applies on this interval from -1 to 1. Well, number one, is it continuous? Is f continuous on the closed interval? That's the first condition. I say, sure it is. How do I know that? Well, this is a polynomial. All polynomials are smooth and continuous, right? And their domain's real numbers, so it's not going to have any issues there. And now the question is it differentiable on the open? Is it differentiable on the open? Is a question mark. Well, let's go ahead and take the derivative. F prime of x would be 3x squared minus 2x minus 2. Notice that the derivative is a polynomial, so it's not going to have any issues either. So it'll be differentiable on the open. So the mean value theorem does apply. And so if you notice in the instructions, if it does, if yes, then find all values on C such that this is true. All right, such that f prime at C. So if yes, f prime at C must equal f of B minus f of A all over B minus A, right? Well, let's go ahead and take the derivative. We already did that, but let's put it in terms of C. So f prime of C is just 3c squared minus 2c minus 2. And we're looking for the C value that makes this, right, in terms of the picture. We're looking for that C value that's equivalent to the slope through those endpoints A, B, right? That's what we're looking for. So let's go ahead and plug in f of B. And A and B, this is my endpoints. -1 to 1 is my A and B. I'm going from -1 to 1. That's my A, that's my B. So f of 1 minus f of -1 all over 1 minus -1. So I got 3c squared minus 2c minus 2 equals f of 1. Plug that into my original. Here's my f of, plug 1 in. I get 1 cubed minus 1 squared minus 2, so I got -2. Plug in f of -1 is 0 over 1 plus 1, 2. So I got 3c squared minus 2c minus 2 equals -2 over 2 is -1. So let me add 1. Both sides equals 0. Let me come over here. 3c squared minus 2c minus 1 equals 0. That'll factor into, let's see, 3c plus 1, c minus 1. Set each of those equals 0, so I'd have -1/3 and 1. So both of those c values would work. Let me give you a picture of this in Desmos. Here's my original x cubed minus x squared minus 2x. Here's my original, and it went through -1 to 1. There it is going through -1 to 1. So there's that slope in blue. Now if we, the C value ended up being 1/3 was one of them. So here's the line for 1/3. You see how the green one, which goes through a -1/3, is parallel to that blue one, right? And then our other C value was actually at 1. And notice it is the original 1 anyways, right? There's that tangent already going through. So there's a visual of that one. All right, let's keep going. Can it be applied on this one as we go from 2 to 4? Well, if you think about here's the natural log of x. We're just shifting this natural log of x 1 to the right. So is it continuous from 2 to 4? Yeah, here's 2, here's 4. Yeah, it's continuous. Those is smooth. It'll be differentiable as well. But let's go ahead and take the derivative just to double check. So derivative of the natural log is 1 over that times the derivative of x minus 1, which is just x minus 1. So 1, it would not be differentiable at 1. But we don't care because it just has to be differentiable on the open interval from 2 to 4, right? Which it is. So it does meet the conditions. So let's go ahead and do it. F prime at C equals f of B minus f of A all over B minus A. F prime of C, we already took the derivative. I'm just going to make it a C instead of an X. F of B, we're going from 2 to 4. So here's my A, here's my B. B is 4, A is 2. All right, so this is saying from here to here, find that slope. So what's the C value in between them that gives you the derivative of this tangent that's equal to the derivative the slope of those secant? 1 over C minus 1 equals f of 4. I'll plug 4 in. I get natural log of 4 minus 1, so natural log of 3 minus ln of 2 minus 1, which is natural log of 1 over 2. Well, the natural log of 1 is 0, so I got natural log of 3 over 2. I'm going to go ahead and cross multiply to solve this. Let me erase this stuff so I got a little room. So I got 1 times 2 is 2. I got natural log of 3 times C minus 1. So I got C ln of 3 minus the natural log of 3 equals 2. Add the natural log of 3 to both sides. So I got 2 plus the ln of 3 equals C ln of 3. I'm going to divide by that number, the ln of 3. And so C is 2 plus the ln of 3 all over natural log of 3. Or you could punch that in. Let's see if I have that here. And notice that is in the interval from 2 to 4. Right? That's that C value that's in there, between there. All right, let's take a look at this one. We got 2 sine x plus sine 2x. Well, 2 sine x and sine of 2x, both of those are continuous on their whole domain. So 0 to pi is not going to be an issue. Let's go ahead and is it fine on the derivative? Well, if you take the derivative, you get 2 cosine x plus cosine 2x chain rule times 2. So we got 2 cosine x plus 2 cosine 2x, and that's our derivative, which will also be, cosines continuous, cosine 2x continuous, smooth and continuous, right? So we're not going to have any issues as far as differentiability is concerned. So the mean value theorem does apply. So let's go ahead and take f prime of C equals f of B minus f of A all over B minus A. We took the derivative. Here it is. I'm just going to make a C there instead of x, equals f of pi minus f of 0 over pi minus 0. And so we've got 2 cosine C plus 2. And I'm going to use, you may have forgotten the double angle formula. But one of them was the cosine of 2u was 2 cosine squared u minus 1. I'm going to use that one. There's 3 of them. But I'm going to use that one. They are listed on your formula sheet because I want to stick with cosines. All right, so let me replace cosine 2c with that. So I have 2 cosine squared c minus 1 equals f of pi. So let me go over here. Let's see what pi. Let me plug pi in. I got 2 sine of pi plus sine of 2 pi. Well, sine of pi is 0. Sine of 2 pi is 0. Looks like that just ends up being 0. Minus f of 0. I plug 0 in now for looks like I get 0 again over pi minus 0. So it looks like I just got 0 on the right hand side. So I got 2 cosine c plus, let me distribute that, 4 cosine squared c minus 2 equals 0. Let me write that in order. 4 cosine squared c plus 2 cosine c minus 2 equals 0. Let me take a 2 out. And so I'd have 2 cosine. Let me factor this. Think about this is just like, this is quadratic in form. It's just like factoring 2x squared plus x minus 1. So I know that's going to be 1, 1. That's going to be a plus. That's going to be a minus. Double check that. 2 cosine squared plus 2 cosine minus 1. There we go. Equals 0. Now I have my factors. 2 cosine c minus 1 equals 0. Cosine c plus 1 equals 0. Cosine of what is negative 1? I say I know the cosine of pi is negative 1. Add 1, divide by 2. Cosine of what is a half? I'd look on my unit circle again and say, well, that's got to be a pi thirds, right? Cosine of pi thirds is a half, because I got to be, I'm looking in this interval just from 0 to pi, right? Between 0 and pi. So both of these would be my interval. All right, let's see if this mean value theorem can be applied for this interval from 0 to 1. Notice if I plug 0 in, I get square root of 0. If I plug 1 in, I end up getting also a square root of 0. So those are both fine. I could plug in values between them. It's going to be continuous. I could not plug in like negative 1, right? That would not work, of course. So yes, it's continuous. How about the derivative? Is the derivative okay? Well, here's the original. Let me actually distribute the x. So I have x minus x squared to the 1/2. Now let me go ahead and take that derivative. So I got 1/2 x minus x squared. Now it's to the negative a half, half minus 1. Derivative of the inside, though, is 1 minus 2x. So I got 1 minus 2x over 2 square root of x minus x squared. That's my derivative, or if you want to put it as 1 minus 2x over 2 square root of x times 1 minus x. It's the same thing, right? 0 would not work. It would not be differentiable with 0, but we don't care because it only has to be differentiable on the open. 1 would not work either, but again, between them I'm okay though. We just care about being differentiable between 0 and 1, right? So let's go ahead and apply the mean value theorem. So f prime of c. So I've got 1 minus 2c over 2 square root of c times 1 minus c equals f of 1 minus f of 0 over 1 minus 0. If we throw the 1 in, I would have 1 times 1 minus 1, 0. So I'd have square root of 0. So I'd have 0. If I throw 0 in, I get 0 times 1 minus 0, square root of 0. And so what would make this true? Well, if my numerator is 0, then this would be true because 0 over anything is 0, right? Add 2c to both sides, divide by 2. So c being a half, make sure it's in my interval. Of course it is, between 0 and 1. And that's the c value that would make, which has a derivative whose slope of the tangent's 0, right? In this case, equal to that slope of the secant. Well, that's it. I hope that helps with the mean value theorem. Thanks so much for watching. Take notes. See you next time.